In Chapter 6, Part 4, Electron Configurations, we're going to start to think about where do the electrons go in a specific orbital for a specific element. So the majority of electrons, or this should say the majority of elements, have multiple electrons, and these all have a specific configuration. So there are a couple of rules and terms as we go forward that we want to think about. But as we add electrons, so for lithium, it has 3 electrons. And the orbitals are the 1s and the 2s. And so when we fill electrons, we put 1 in at a time. And so each one of these is equal to 1 electron. And so you'll notice that mine are single barbed arrows. It is either 1 this way or this way. We do not see this. This is a big no. So the single barb means that as a single electron. The double barbed, in fact, means something quite different in chemistry. So just make sure that you're drawing the right type of arrows. And so as we add electrons, we're going to talk about core electrons, which are electrons that are in a filled shell, and valence electrons. These are electrons in a partially filled shell. So for lithium, the 1s would be a core, and the 2s would be valence. And so as we think about this, we're going to think about filling them one at a time. So let's talk about Hund's rule. And it says for degenerate orbitals, the lowest energy is obtained for 1 electron in each orbital and all electrons having the same spin. So our up arrow and our down arrow mean that they have different spins. So degenerate orbitals are things like the p orbitals, the d or the f orbitals. So it is not the s orbitals because there is just 1. So basically, degenerate orbitals are anything with an m sub l other than 0. So for the p orbitals, we have the px, py, and pz orbitals. And so the lowest conformation of energy is when any group of electrons all have the same spin and every orbital gets a single electron. And so as we learn to fill these, it's important to remember this rule. And so this tells us how to fill electron orbitals. And so what we're going to look at next is basically a bunch of elements and see if we can start to figure out patterns. So when we look at lithium, which we just did, it has 3 electrons, in the 1s and then the 2s. And so you just add in 3. So for beryllium, it has 4 electrons, in the 1s and the 2s. And so you could also, so this over here is called drawing. And if you'd like, you can write out the configuration. And it's 1s superscript 2, 2s1, 1s2, 2s2. So you can draw and write this for any given element. And so let's look at a couple more. So for boron, which has 5 electrons, 1s, 2s, 2p, 1, 2, 3, 4, 5. Now you could have selected any of these p orbitals to put your single electron in. You can put it in any one, and it could have gone down. So let's look at carbon, which has 6 electrons, 1s, 2s, 2p, 1, 2, 3, 4, 5, 6. So keep in mind that we need to follow Hund's rule at all times. So 1s2, 2s2, 2p2. So as you noticed on boron, when there was 1, you could include the 1 or not. It's somewhat by default assumed that there is a 1 there. So let's think about neon, which has 8 electrons. Neon has 10 electrons. 1s, 2s, 2p. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1s2, 2s2, 2p6. So next let's look at sodium, which has 11. So one more electron. 1s, 2s, 2p, which actually has 3, and then the 3s. And so we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so you could write this out as 1s2, 2s2, 2p6, 3s1. So and you can do this for any element. And so let's go ahead and think about that for potassium. So potassium has 19 electrons. 1s, 2s, 2p, 3s, 3p, and 4s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Now you'll notice that I always fill my electrons using Hund's rule when we get to the p orbitals. And so the other thing you're probably thinking is, whoa, this is getting long. So it's long, even if you write it out. So it turns out that we can, these are going to get super long as we really move down the periodic table. So you can use a noble gas configuration. Where you can annotate something that looks the same. So it turns out that the closest previously encountered noble gas is argon. And so argon has 18 electrons. And so argon's 18 electrons are in the 1s, 2s, 2p, 3s, 3p. And here are those electrons. Whoops. So we can basically say that for potassium, it looks like argon, 4s1, or argon, 4s. So this just basically says that we have an argon core, and this is our valence. So as we move forward in this semester, the distinction between core and valence electrons is going to become quite important. And so both of these cores, or in any case, it's going to be the previously encountered noble gas. So the best way to think about that is if you look at your periodic table, don't forget that your noble gases are here. And so if this is your element, you would go back and this would be on the row ahead, or the row above. This is your noble gas core. And that is true in any case. Even if you are way over here, you would go back all the way until a previous n number. So it would be, if you're N4, it is the N equals 3 noble gas. And so we can see that electron configurations are pretty similar if we look at potassium and sodium. Sodium has a noble gas core of neon and the 3s1. And so we can see that those look like this to one another. If you think about a transition metal, so let's look at manganese, which has 25 electrons. And so the closest noble gas in that case is going to be argon. And then we have the 4s. And then we encounter the 5,3d orbitals. So argon has 18 electrons. So that leaves leftover 7. So they would look like this, to where 2 in the s orbitals and 5 independent orbitals in the 3D. So it turns out that the 4s is lower in energy than the 3D. And so it will be filled first. So you might be wondering, how on earth am I going to remember how to fill all these orbitals? So it turns out that there are a couple of different ways that we can start to think about that. There are a couple of different patterns that we can think about as we learn to fill these. So the way I like to think about this is to make this graphic. 1s So this graphic lists out all of the orbitals. P, D, for F, 6s, 6p, 6d. So in this case, I'm going to draw in red what we do. We're going to draw diagonal lines and fill this first, third, fourth, fifth, sixth, seventh. So you can fill them in order of 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, etc. So this is well and good. But I think one of your other questions is probably, so what do we do with this and how do I know where the electrons are? Do I just remember all of this, or does this relate to the periodic table? So if we were to draw a periodic table, which I'm going to do to the best of my ability, and it will be only moderately to scale. But we can basically say, it turns out that the electrons can be identified in blocks. So we have the s orbitals over here where there are just two rows or two columns. The p orbitals are on this block where we often find the nonmetals. And so if you were to go across one row, there are 6 columns. This is the noble gas. And so in the middle, these are our d elements, or the d orbitals. And there are, in fact, 10 of these. And down here at the bottom, these are our f orbitals. So this is helpful. And as we think about these, so I'm going to redraw this because I kind of doodled all over that one. So in this redrawn periodic table that looks something like this, we can identify the s element being over on the left and the p element or the p orbitals being on the right. So how do we go about filling this? Well, it turns out that you can just fill them as you go across. And so what the other thing is that we can think about is that as we go down the periodic table, the n equals 1, 2, 3, 4, 5, 6, 7. So for the n equals 1, you fill it across. For the n equals 2, we would encounter the s and then the p elements. For the n equals 3, and you would fill that across. Then we see the s and the p, s, p. But this right here is the 3d electrons in the next row. So the 3d electrons are not next in order after the 3p orbitals. They come after the 3 or the 4s. And then we have s. This will be the 4d, p. SS, 5D, 6D. And this is the 4F and the 5F. Now, if you're starting to say, I just really don't know how to, this just is too much. The other thing, if you're looking at your periodic table, is that the number of electrons counts up as you go across. So as you go across any row, they count up. So the F elements, there's a place left for them right here. And so sometimes you'll see periodic tables where they're inserted in there, but you can fill any set of electrons based on this graphic. Between this and the diagrams I drew on the previous section, you can basically figure out the order as long as you know how many electrons there are. So for any element, you could look at its location on the periodic table and say, I know where that element goes and how many electrons it has. So there are a number of elements that do not follow the rules. So these are the rule breakers. And so I have tried to highlight these in pink. So it turns out that many of these follow patterns. So for chromium, it turns out that it is more energetic for the 4s and the 3d electrons. So there are 1, 2, 3, 4, 5, 6 valence electrons, and they go 1, 2, 4, 5, 6. 1, 2, 3, 4, 5. So there are 5d orbitals, and that is lower in energy than the alternative, where you could move them across. So we see something similar if we look at the almost fully filled d orbitals, which would be here. So you'll notice that a lot of these would be the difference between a half filled and an almost fully filled. So if you look at copper, which also has the 4s and the 3d, and so for those 10 electrons, it is better to have a fully filled d orbital than to leave one electron out of the d orbital. So it will move one from the 4s to the 3d. So these highlighted in purple or magenta are rule breakers. And so I will ask you on exams and in other places about the d element violations. The pattern for which the F block elements violate this filling rules, in my opinion, are kind of complicated. And so you can go ahead and kind of think about that, but the rule breakers are pretty important. So the first thing we want to do is write and draw the electron configuration for calcium. So calcium has 20 electrons. And so we know that they fill 1s, 2s, 2p, 3s, 3p, and 4s. So then we can just start putting them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we've used all of our electrons, and they are 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So in this case, it's not necessarily a trick, but the objective is to remember the order in which the orbitals fill, and then you can count the electrons. So what about for chlorine? Chlorine has 17 electrons. And so we have the 1s, 2s, 2p, 3s, 3p, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Now, you could have also drawn your 3p to look like this, or like this. So there is nothing that says which one has to be empty. I tend to leave it last, but any of those are acceptable. So we could write that out as 1s2, 2s2, 2p6, 3s2, 3p5. So the writing, if I ask you to write it out, looks like this. So this is a write. And up here where we've drawn the arrows, this is the draw. So let's look at another example, maybe something a little bit more complicated. So molybdenum. This has 42 electrons, so that means it's going to take a while. So we should start by putting out some orbitals. So based on the periodic table, we know that it's going to go through 4D. And so if you look back a couple of minutes, I drew on there which ones they are. And so if you can start to learn where they are in the periodic table, it'll make it easier to predict which orbitals you need. Oops, that's not the 4s. This is, in fact, the 4p, 5s, 4d. So now we start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42. So molybdenum, if we look at what we see here in the 5s and the 4d, this doesn't look very balanced. So it turns out that we are going to promote the electron out of the 5s to give us 5s1 and 4d5, because this is lower in energy. If everybody has their own seat, then it is lower in energy than anyone sitting together. So when you would write that out, you would write it as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d5. There are different scientific arguments as to whether or not the d and p orbitals change arrangement, or the s and d. So there are some people who switch these two. I will accept it either way. There are justifications for either way at different times. So let's look at one more example, Pb, which is lead, which has 82 electrons. So in this case, I'm going to use the noble gas configuration. On the exam or any assignment, I will give you, it will directly say you can or you can't. So the previous one is going to be xenon. And then I'm going to go ahead and draw out all my orbitals. So now that we have all of our orbitals drawn, we need to figure out how many electrons need to go in there. So 82 minus 54 that are accounted for the xenon core is going to give us 28 electrons. And so from here, we can start putting these in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So in this case, if we were to write this out, it would be the xenon core, 6s2, 4f14, 5d10, and 6p2. So again, it will tell you whether or not you should use the noble gas configuration or not, but you do need to memorize the order in which they are filled. It is easiest to do that by memorizing where the location is on the periodic table, like we talked about earlier.